Okay, we're now recording. All right, and share the screen. Okay. All right, question was asked about your grade. You can always email me for your grade, but you theoretically can always figure it out yourself. Okay, you know my grading scale, you know your scores, you know your quiz scores, and theoretically you should be able to always figure that out. But otherwise you can email me. Okay, so we're up to here, 3.7. It's all word problems. I'm going to do a lot of them. It's applied situations for finding the derivative in economics and the sciences, biology, chemistry, physics, examples of those. Okay, so I'll be showing you as many of those as I possibly can. There's no new formula, no new derivatives for this one, just applying what we've done. Okay, so it was 7 to 19 odd. I'll do as many as possible today. So 7 through 19 odd. All right, so as usual, I'll show them to you. Page 233. Here's 7, 9, 11. It's hard for me to get the bottom of 11. Turn that up. Okay, there we go. I know I'm going through it fast, but again, this is for those of you who don't have the book. As long as it shows up even for less than half a second or something, you can always go to the video and fast forward, pause as necessary. 17 and 19. Okay, so I think I've given you everything you need there. All right. Okay, so the topic is rates of change in the natural and social sciences. So we're giving you applied situations where the derivative might show up in biology, chemistry, physics, and so forth, right? Okay, number 7, we've actually tackled some of this kind of problem before. Okay, the height of a projectile, blah, 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 just jump straight to the formula. H is 2 plus 24.5t minus 4.9t squared. Okay, A, velocity. Velocity means first derivative. Okay, acceleration is second derivative. We know that. Okay, and it talks about maximum height and all those kinds of things. Okay, so let's see what we can do with that. All right, so here's the height function, 2 plus 24.5t minus 4.9t squared. Okay, so the first derivative is 24.5 minus 9.8t. That's the velocity. Okay, so again, velocity is the first derivative of the distance function, or in this case, it's a height function. You're throwing an object up in the air and it comes back down. Okay, so it asks for the velocity after 2 seconds and the velocity after 4 seconds. So I just plug in to the velocity function. So plug in 2, 24.5 minus 9.8 times 2, 4.9 meters per second. Height is given to be in meters. Time is given as seconds, so velocity is meters per second. Okay, V of 4, just plug in 4. Negative 14.7 meters per second. All right, so what's the significance of the negative? Negative means it's going down, right? So after 2 seconds, it's still going up, 4.9 meters per second. After a certain amount of time, it stops and comes back down. It's coming down at 14.7 meters per second. Okay. In order to do B, when does a projectile reach its maximum height? Okay, so maximum height. So if you think of an object that goes up and then comes back down, if you're at the maximum height, the velocity is 0, right? It stops ever so slightly. So it's going up, positive velocity, stops at that highest point, and then it starts to come back down. So when a projectile reaches its maximum height, the velocity is equal to 0. So to work that out, set V equal to 0. Okay. So maximum height, once more time, goes up, comes down. So right at the very top, velocity is 0. All right, so I solve the velocity function, h prime or v, 24.5 minus 9.8 t, set it equal to 0, 2.5 seconds. Okay, so this object goes up, and then after 2.5 seconds, it reaches the top, and then it starts to come back down. Okay, and then C, what is the maximum height? Plug in the height after 2.5. Okay, this is the distance function in general. What's the maximum height? Plug in 2.5. So 2 plus 24.5 times 2.5 minus 4.9, 2.5 squared. Punch it in a calculator. Again, I will save time and just tell you what it is. 32.625 meters. Okay, so this object goes up to a height of 32.625 meters at the highest point, and then it comes back down. Okay. All right, D. 7D, hit the ground. What's true when it hits the ground? The height is 0. So I set the height equal to 0. So I put 0 equals negative 4.9 t squared plus 24.5 t plus 2. To make it a little bit easier on myself, I multiply both sides by negative 1. Okay, so I get this, throw it in the quadratic formula. So I just said, et cetera. Again, et cetera is something that I'm allowed to write, but you can't on, quizzes or homework or tests. You work it out, but just use the quadratic formula. Okay, so you finish the rest of that on your own. Quadratic formula. I'll throw out any negative values. If any t comes out to be negative, then you eliminate it. And then E, with what velocity does it hit the ground? Okay, so take the answer you get in D, you get a certain time, right? And then plug it into the velocity function. Okay, so I'll just tell you that. I can't really write it right now, but you can jot it down if you want. So the answer to D, let's pretend it comes out to be t equals, I don't know, 5 seconds. Okay, so let's pretend the answer comes out to be 5. I don't think it is 5, but let's say it is 5. Okay, then take that 5 and plug it into the velocity function. Right over here. Okay, so that's how you do that one. Okay, yeah, anybody who joined late, go ahead and put your name in the chat and I'll get you for attendance later. All right, so that's how to do that one. And number 9 is very similar, so I'll let you do number 9 on your own, I think. Okay, number 9, if a rock is thrown vertically from the surface of Mars with velocity 15 meters per second, the key thing is this formula here, right? Height is 15t minus 1.86 t squared. Okay, so you can figure out the rest of that. So velocity, take the derivative. Okay, first derivative, and then plug in 2. All right, so I'll let you try the rest of that, but I will now go to focus on problem number 11. That looks like it's a little bit more complicated. Okay, 11. A company makes computer chips from square wafers of silicon. It wants to keep the side length of a wafer very close to 15 millimeters and wants to know how the area A of X of a wafer changes when the side length X changes. Find A prime of 15 and explain its meaning in this situation. Okay, so what do they want us to do there? All right, so you're working for a Silicon Valley company. Okay, you're making chips that are supposed to be square, roughly 15 millimeters. Okay, but in general, let me call it X. All right, so we know the area is X squared. Then using the Leibniz notation, again, L-E-I-B-N-I-Z, Leibniz notation, dA dx is equal to 2x. Okay, a nice thing about having the Leibniz notation, It means the rate of change of area with respect to x. So if I change x by a certain amount, how much will the area change? And in this case, it's going to be 2x. Okay, they want a prime of 15, it says. So I just plug in 15. 2 times 50 is 30. Okay, the units technically should be millimeters squared per millimeter. I know that sounds funny. If you do the cancellation, you would say 30 millimeters. But to me, it's actually more meaningful to say 30 millimeters squared per millimeter, i.e., if I change the x by 1 millimeter, the area changes by 30 square millimeters. Okay, so mathematically it's 30 millimeters, but to me it makes more sense to say 30 millimeters squared per millimeter. Okay, so right when x is 15, the rate of change of the area is 30 square millimeters per millimeter change in the x direction. Okay, so that means if I change this by 1 millimeter, the area should change by roughly 30. Okay, and there's my language of it. They asked for the interpretation. At a length of 15 millimeters, a change in length of 1 millimeter would change the area by about 30 millimeters squared. Right, so that's that. Then part B. Show that the rate of change of the area of a square with respect to side length is half the perimeter. Okay, it's actually easier than you think. You just have to know what it's talking about. The rate of change, i.e. derivative, is half the perimeter. Well, just do it. What's the perimeter? 4x. What's half of that? 2x. That was the derivative. We're done. We've shown it. The rate of change, the derivative, is half the perimeter. So we got it right there. Okay, and what's the rest of this picture that I got there? So now it's a little bit of geometry. Try to explain geometrically why this is true by drawing a square whose side length x is increased by an amount delta x. How can you approximate the resulting change in area delta A if delta x is small? Okay, so what do they mean by that? Okay, so here's the original picture. Okay, here's x. Now they're saying increase the side length by a tiny amount, delta x, but it stays a square. So you have delta x here and delta x here. So the increase in the area is the shaded region that I have in red here, right? The original was x by x. Now it says if I increase by delta x on both sides, what's the change in area? So the change in area is the red stuff. Don't include this because that was originally there. The new stuff is what I have in red. Okay, so it looks like I have 3 rectangles, this one, and this one, which is actually also a square. Okay, so this is x by delta x. Here's another x by delta x. And this is delta x by delta x, or delta x squared. Which means delta A is 2x delta x. I got 2 of these, right? So delta A is 2x delta x plus delta x squared. Okay, so if I divide both sides by delta x, that one cancels out. One of these cancel out. So delta A over delta x is 2x plus delta x, algebraically. And now you can see as delta x approaches 0, which is what they said in the question, delta x gets really, really, really small. That means this distance and this distance get really, really approach 0. We have dA dx would be 2x plus nothing. If delta x approaches 0, then that drops out. And we have 2x, which is indeed what we were looking for. So the rate of change of the area with respect to x in the limit as delta x approaches 0 is 2x, i.e. as this picture becomes delta x is really, really tiny, right? Then this square gets insignificant, becomes practically zero. So the net change in area would just be the amount from here plus the amount from here, because this part ends up approaching zero. Okay, so that's what we have for that one. Okay. All right. So that's the idea behind a lot of these problems. Just take the words and change into a calculus question. Okay, so how about 13? Set you up for that. Find the average rate of change of the area of a circle with respect to its radius r, as r changes from 2 to 3, 2 to 2.5, 2 to 2.1. Find the instantaneous rate of change when r is 2, and show that the rate of change of the area with respect to its radius is equal to the circumference of the circle, blah, 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 blah. Okay, so this is almost like back to 2.1, average rate of change. You're fixing the 2. See how it's always a 2? And then it looks like you're approaching 2 coming only from the right side. 2 to 3, 2 to 2.5, 2 to 2.1, right? So the approximation to the tangent gets better and better, right? Okay. Right. So I made myself a little table here. R and area is pi r squared, right? In this case, it's easier to just leave it as pi. Don't type in 3.14 or whatever. So radius is 2, 4 pi. 2.1, 4.41 pi. 6.25 pi. 9 pi. Okay. Now you say, where did you get these numbers from? Those are the numbers they told me to. They said go from 2 to 3, 2 to 2.5, 2 to 2.1. So I needed the y coordinates for each of these, right? Okay, so AI asks for the average rate of change from 2 to 3. It's just y2 minus y1 divided by x2 minus x1. It's 2 comma 4 pi and 3 comma 9 pi as my points. Right, so y2 minus y1, 9 pi minus 4 pi, divided by x2 minus x1, 3 minus 2. So it comes out to 5 pi. So the average rate of change going from 2 to 3 is 5 pi. Average rate of change of the area with respect to radius, as we say. Okay, then it said do the same thing, 2 to 2.5, 2 to 2.1, right? 13, A2, 2 to 2.5, 13A3, 2 to 2.1. You're fixing it 2. You're making that second point come closer and closer and closer to 2. And we're seeing what happens to the slopes of those secant lines. They're going to approximate the slope of the tangent line, as we have seen before. Okay, 2 to 2.5. Y2, Y1. 6.25 pi minus 4 pi. Divided by x2 minus x1, 2.5 minus 2. Punch it in your machine, 4.5 pi. Same thing from 2 to 2.1. We're just coming closer. Right? Remember, 2 is fixed, and we're moving 3 into 2.5 into 2.1. We're getting closer and closer. So I find the slope. Pretend these are my ordered pairs. Right? Pretend it's parentheses, right? Parentheses 2 comma 4 pi parentheses 2.1 comma 4.1 pi, right? So same thing. Y2 minus y1, 4.41 pi minus 4 pi, divided by 2.1 minus 2. Okay, punch in a calculator, 4.1 pi. Okay, now, before we even knew anything about derivatives, we could just look at this and say guesstimate, right? We're coming closer and closer, right? 2 to 3, 2 to 2.5, 2 to 2.1. Does it look like we're approaching anything? 5 pi, 4.5 pi, 4.1 pi. Looks like we're getting very close to what? 4 pi. Okay, so the second part of the problem, find the actual instantaneous rate of change. We know how to do that, find the derivative now. Okay, so what's the derivative of pi r squared? Remember, pi is a constant. It's like saying 3.14 r squared. So the 2 comes down, hits the pi, call it 2 pi r. Plug in 2, 4 pi, just as we anticipated. Looking at the progression, 5 pi, 4.5 pi, 4.1 pi. Oh, looks like we're getting close to 4 pi. And that's confirmed. The actual derivative is indeed 4 pi. Okay, now the other part of the problem. So that was part B. C, show that the rate of change derivative. So when it says rate of change like that, it's derivative, is equal to the circumference of the circle. Well, here's the formula for the area. Right? Do you remember what's the formula for the circumference of a circle? 2 pi r. And it says, show that it's equal to the derivative. Here it is, the derivative is 2 pi r. Okay, that's interesting. The derivative of the formula for the area, the famous formula that you've had since, I don't know, when did you first get this? 5th grade, 6th grade, 7th grade, something like that. Okay, and you also had the formula for circumference back then, 2 pi r. Turns out the derivative of the area formula, pi r squared, is the formula for the circumference, 2 pi r, right? The derivative of pi r squared is 2 pi r. And then they're actually asking you to show that geometrically, so it's not as surprising as you might think. Okay, so they want a geometric argument, just like I did this thing geometrically. Okay, they did ask for 2. So a prime of 2 is 4 pi. We already did that. Okay, so why is it reasonable that the change in area, the rate of change of the area with respect to r, is the formula for the circumference of the circle? Okay, so here's my picture of the geometry. So here's a circle. Say increase it by a small amount, delta r, right? So here's r plus delta r. So once again, just like I did over here, the game that I'm playing is the red stuff is the new area. So here the red stuff is the new area. Okay. I'm trying to find the increase in the area. This was already there, so I don't shade that. Likewise over here, this was already there, so I don't shade that. This is the new stuff. Okay. Now, imagine I get a scissors, cut right here, cut it and open it up. Okay. I have this almost rectangle. It's not really a rectangle, but it's kind of like a rectangle. Here's the picture. Can you visualize this? Okay. One more time. Take this thing, get a scissors, cut it, open it up. It ends up looking like this. Not quite a rectangle, but it looks more and more rectangular-ish if delta r approaches 0, if it's really, 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 really small, right? Which means the approximation gets better and better and better. So what is this vertical height? Is a tiny amount, it's delta r. Now, see if you can imagine this. If I cut here and open it up, this length is going all the way around, right? Well, that's the formula for the circumference of a circle, 2 pi r. Now, granted, you're right. There's actually 2 circumferences. There's a slightly bigger one and a slightly smaller one. That's why I made it like this, right? Okay, the inside circle is a little bit smaller than the outside circle. But the whole idea, again, is that delta r approaches 0. If delta r approaches 0, this gets scrunched down more, so the top and bottom look practically the same, right? So this is 2 pi r. This is delta r. Okay. So my delta A, my change in area, is approximately, not exactly because it's not a true rectangle, but it's length times width. What is this length? It's the circumference of the circle. If I cut and open it up, it's 2 pi r times delta r. Divide both sides by delta r. And if delta A over delta r is approximately 2 pi r. But as delta r approaches 0, the approximation gets better and better and better. It looks more and more rectangular-ish, so that in the limit, we can go ahead and say that DADR is indeed 2 pi r, just as we expected. Okay, so it does seem reasonable. Right, so that's interesting. The derivative of the formula for the area of a circle comes out to be the formula for the circumference of the circle. Okay. All right. Then let's see. Next one I want to show you was $15. This should not be that hard. A spherical balloon is being inflated. Find the rate of increase of the surface area, S equals 4 pi r squared, with respect to the radius r, when r is 1, 2, 3, what conclusion can you make? Rate of increase of the surface area. Okay, so you have a balloon, you're blowing air into it, it gets bigger and bigger and bigger. So as you put air into it, the surface area obviously increases, the volume does also. Okay, and they want you to say something about the rate at which the area is increasing after so much time. Okay, so let's see how to do that. Okay. So formula, surface area is 4 pi r squared. So how does the surface area, which I'll call S, change as the radius changes? So I take the derivative, ds dr, rate of change of surface area with respect to r, 8 pi r. Well, I just plug in 1, 2, 3. Plug in 1, 8 pi. Plug in 2, 16 pi. Plug in 3, 24 pi. Again, look at the weird units I have. Feet squared per feet. So I suppose you can cancel out one of the feet and say 8 pi feet. But again, I think it's easier if you just say 8 pi square feet per foot. Okay, meaning if I change the radius by 1 foot, the surface area increases by 8 pi square feet. Same thing here, same thing here. All right, and then they say something about what conclusion can you make? So what conclusion can you make? Well, what happens when r increases? 8 pi, 16 pi, 24 pi, right? So as r increases, dsdr also increases. Okay? So as time goes by, your rate of increase of the surface area also goes up when the radius goes up. That's all. Okay. The idea being, as you're blowing up a balloon, okay, so the increase in surface area is pretty small at the beginning, but after a while, okay, as it gets bigger and bigger and bigger, the rate of increase of the surface area, you know, grows just as fast as the increase in the radius goes also. Okay. All right. Then let's see. Okay, then the last one I was going to do was 19. I'll let you try to figure out 17 on your own. The mass of the part of a metal rod that lies between its left end and a point x meters is 3x squared. Find the linear density when x is 1, 2, and 3 meters. Okay, so it says look at example 2, but I'll let you figure that out on your own. But I wanted to show you 19. And then I'm pretty much done with the section. Okay, I'll give you one to try on your own, and then that'll be it. Okay, so number 19. The quantity of charge in coulombs that passes through the point is given by Q of t is t cubed, blah, 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 blah. Find the current when t is 0.5 seconds and t is 1 second. Okay. The unit of current is 1 ampere, 1 coulomb per second. Okay, so current is a measure of the amount of charge that passes through a point at a given time. Okay, it's the derivative dq dt or q prime. Okay, and then it says at what time is the current lowest. Okay, so let's see that. Oops. Bear with me just a second. Gotta get something down here. So here's a charge function, charge measured in coulombs in electricity. The derivative is the current. So Q prime is 3t squared minus 4t plus 6. All right, then it says plug in 0.5 and 1. I'll let you do that on your own, but you just pretty much do that. Where was it? From 19, right? So plug in 0.5 and 1 to the derivative. And then it says at what time is the current lowest? All right. I can do 1 for you in my head. Plug in 1. Don't plug it into here. Plug it into the derivative. So plug in 1. 3 minus 4 plus 6 is 1. 1 ampere. The lowest current, you want to minimize this. Okay. You might recall this shape is a parabola. Okay, parabolas either open up or down. That's what I'm trying to indicate here. Okay, here's a parabola which opens up. Here's a parabola which opens down. Here it's the highest. Here it's the lowest. If it looks like this, moving upward, then the derivative would be the lowest. So you want the derivative of the current, which really means second derivative. Okay, so I'll just tell you what you do for this without actually doing it. Find Q double prime, set it equal to 0, and solve for t. That's easy to do. Okay, so to do the rest of this problem, okay, I already did 1. Plug in 0.5 there and there. It's a little bit messy, but it can be done. The lowest current, take the second derivative, set it equal to 0, solve for t. So that's my hint for that one. Okay. All right, that's it. I was going to stop and let you do one for the last 12 minutes or whatever, folks. Okay. And when you get your answer, just put the answer in a chat and you can leave. So we're going back to something that I had already talked about a little bit. Okay, so back to page 233, 3.7. Okay, I want you to try 9A, if you would, please. 9A, when you're done, put your answer in the chat and then you may leave. So the main thing that you need is the height is 15t minus 1.86t squared. What is the velocity after 2 seconds? Okay, a proper answer is giving the units. So what should the proper units of velocity be? Okay, in this case, it looks like we've got seconds and meters, so meters per second, right? So how do you find the velocity? Velocity is derivative. So for number 9, take the derivative, plug in 2. Your answer is blah, 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 meters per second. You could put m/s, I suppose, for meters per second, and that'll be it. Okay, I'll give this another 15 seconds or so. So those of you that need it, please take a picture on your cell phone now or do a screenshot. Or if you've got the book, just use the book. 9A, when you're done, you can leave. Okay, 9A, it's basically find a derivative, plug in 2, put the right units, and that's it. And then I'll see you tomorrow. Okay, I'm going to assume everybody has it right now, so I'll make the book disappear. And here we go.